Hey, Arbitrary, how's it going? AC. LBW. I think I know who LBW is at this point. Okay. By elimination. Elimination theory. Oh wow, Crow! Wow. Alright, well good luck with that. Yeah, that's a joke. Oof. That's tough. Not sure intersection theory is gonna help with that, Crow, so I'm sorry about that. Sorry, we couldn't be more help here. Yeah, I think I was the same way, Crow. I think I was the same way. Wouldn't study all the way up until the exam. Oh, okay. What is that, stats? I mean, what's the difference? You don't have to tell me, but I'm always curious. Applied stats? Okay, okay. Got it. Stats programming combo. Nice. Alright, how do I check? If I do something, oh my god. here. This. Okay. Wait, Classic Nations. You're a subscriber. That means you're a relative. Welcome. I'm gonna figure out who you are. Okay, got it. All right, let's just get the stream going. What we need this music. That's right, NC. Okay. These are the things I need to cover in the immediate future. Get a haircut? No, not in the last day. Oh, I know what you're saying. It's a wig. That's the story. It's a wig. Classic Nations. Why would you cut a wig? Exactly. Exactly. This is a wig. Classic Nation. Oh, same glasses? Nice. 5:59. In case any of the Australians are still waking up. Wait one more minute. Hey, Kappa Votes, how's it going? All right. Mm-hmm. Do I do this? Put this on my CV? Hell no. All supposed. I do not. I see what you did there, AC. That's really clever. It's like, yeah, that's good. That's high quality stuff. All right, 6 o'clock. Ready? Here we go. Intersection theory. Ready? Hey, Fembox. So the next topic is of absolute. It's critical that we become fluent with what vector bundles are, how to think about them, how to manipulate them. Okay? And some examples, especially line bundles, vector bundles of rank 1. Okay? So that's what I'm going to do. And some of the things I'm going to talk about today are actually typically supposed to be done in the privacy of your own home. There's a chance that I'll get I'll mess up some indices or something. It's one of those things. So let's see how much I mess this up. It'll be fun. Okay. Hey, Megalomorph. Okay. So I'll start with vector bundles, what they are. I'll begin with the most down-to-earth description of them. Okay. And then from a vector bundle, one naturally gets a sheaf. Now that sheaf is a special kind of sheaf. Those special kinds of sheaves, though, on their own, basically carry the same data as a vector bundle. And so vector bundles, in that way, are encoded by locally free sheaves. Then I'll talk about specialized to the case of line bundles because they're extra interesting. And we'll investigate a couple line bundles that we actually can think about at this point. And once you know what a line bundle is, not just these are special cases, examples. Once you know what a line bundle is, you'll know what a linear system, what it means, what the word linear system means, definition. And the word linear system, that language is used all the time in especially, classical algebraic geometry. Okay? All right, ready? Oh, look at that. This is a really beautiful Kummer surface. I like the color scheme this time. Okay, vector bundle. I'm just gonna stick to the language of varieties. All right? Everything goes word for word with schemes instead. Okay. So, what is a vector bundle? So the first thing I want to say about this is that a vector bundle, when someone says vector bundle, it's a physical thing. It's a physical object. Okay, so let me set it up now. X will be a variety or a scheme. Or topological space. Or C infinity manifold. Or complex manifold. Whatever. Okay, very general situation. Okay, X is a variety for us. So a vector bundle is this. A rank n vector bundle. Is a variety F along with a map to X. Sometimes we call it the structure map or the bundle map or the projection map if the projection word isn't being used in another place. Okay? Is a variety and a map. So it's this data, which is, I'm going to write it in words now. I'm going to write the slang, and then you'll understand the slang. Which is locally on X isomorphic to X cross just ordinary affine space. The projection number 1. That's not it. It's locally isomorphic to this with transition maps being linear. Okay. Hey, pandemic. So what does locally mean for us? We have a topology. We always have a topology here. It's the Zariski topology. If you use some other kind of topology, you need to specify that. And then you'd be talking about that kind of a vector bundle. A vector bundle in the blah topology. All that? Okay, and then I'm going to explain this thing. So here, but this is not a definition. This is telling you what the idea is. All right? Good. Okay. So what do we mean by this? We mean there exists an open covering of X and isomorphisms. In what category? Topological spaces. Continuous map, forward and backward. A regular in algebraic geometry. Polymorphic in whatever. And then C infinity, whatever. It's super general. Yeah, I'm just going to use isomorphism though. There exists an open cover and isomorphisms. These are called trivializations. I'm going to draw a diagram. Isomorphisms phi sub alpha. There exists an open cover of X. And then notice which part of this diagram references the object F. This thing. This thing is in F. It's an open subset of F, right? Because I'm taking a preimage of an open set. So there's this big chunk of F, which is isomorphic to just this product set. And this map becomes pi 1. So I need to put that. Commuting diagram. So that's what locally on X, isomorphic to a product means. That part. And now the transition functions, the transition maps statement. Okay, there exists an open cover, so 1. I'll put a 1 here. And 2. Okay, we're going to use the convention that when I write U sub alpha beta, it means this intersection. If you pull back pi along an inclusion, you get a product. You get a product with projection onto first term. Exactly right. Yes. Yes. Yes, exactly. Yeah. Okay. I was making sure that that is not a circular thing, but yes, exactly right. Okay. So second, okay, 2. That for any alpha beta, for any 2 indices, you get this. You can look at this composite. you can look at this composite. On a grid. What are the grid lines? Yes, inverse. Reverse. Inverse. Because technically my fees were going that way. Exactly right? Yeah. Yeah. That's correct. Correct. Okay. So, that the composite map, which we'll call G sub alpha beta. Now this map's an isomorphism, but you asked that the composite map is represented an n by n matrix invertible whose entries are regular functions on U of alpha beta, or continuous, or holomorphic, or C infinity, or whatever. Whatever your subject is. Okay? Does this make sense to everybody? The way we write this is, where would you read it? What is a regular function on U alpha beta? It's just an element of the structure sheaf. This is a ring. You have a ring of functions specified. When you have a scheme, this ring that's there for you. It's already part of the data. Okay, and so we just write GLN of Is this okay? Okay. Notice that this G of alpha beta, if you just think about what it's doing on points, like look, if you think of a point as p comma n tuple of numbers, whatever it does, whatever it outputs, it's got to have the same first entry, p. It can't change the p part. That's because all of these things commuted with first projection maps. Okay? There's got to have a p there. But then, the point is, which n tuple of number, how do I place an n tuple of numbers as the output n tuple? It's a linear transformation applied to a1 up to an. It's like a vector, or think of this as a vector. It's some matrix applied to. It's a linear transformation, not an arbitrary map from an to an. There are so many isomorphisms from an to itself. In fact, there is in some sense no classification, clean classification of the automorphism group of an. That's a very old story I won't go into. Okay, but we're asking just make it a linear map, the best kind. And this matrix, it depends on p. It varies with the point p. And how does it vary? In a regular way, polynomial, in a holomorphic way, in a C infinity way, just a continuous way, whatever your subject is, in a way that's according to this ring. Those are the entries of this. The matrix entries are functions. They are regular functions for us. Notice that they're regular functions they only need to be defined on this intersection. They don't need to be defined on all of X or only on U alpha or only on U beta. They just have to be defined on that intersection. Number 1, you arranged the 4 in a grid pattern or a square with the transforms or mappings perpendicular. No. There's nothing about that. No. I could have made the arrows curvy. It's just data, and it doesn't. There's no geometry in the arrows. All right, good. So, yeah, it gets placed this way because typewriters are easier to type vertical and horizontal. I mean, that's why it is. Okay. Now, okay, that's what a vector bundle means. It is a physical object. A physical object that's locally modeled on the product of affine space of dimension n, if it's a rank n vector bundle, with the base x. And the what we call the transition maps, these G alpha betas, and you should think of this as a transition function from transitioning from U alpha to U beta. But it's not. It's only defined on like over the intersection, the overlap. Now I'm just drawing a cartoon of two open sets and an overlap. This G alpha beta transition matrix is kind of, the data is over there. Okay, and in algebraic geometry, two open sets will never look anything like this because in the Zariski topology, open sets are enormous. Just remember that always. It's just cartoons to organize data in your mind. Any questions about what a vector bundle is? All right. So next, I'll just keep looking at Discord and things if you want me to slow down. So next, suppose we have a vector bundle. Okay? If you right, if we had a totally disconnected space, 2 becomes vacuous then. No. I think 2 is still needed. Two is still needed because, for example, an affine transformation, like just like shifting affine space by a vector, that can never be used as a transition function in a vector bundle. That's some other kind of bundle, maybe an affine bundle or something. So saying that the transition functions are linear is going to be a requirement always for any kind of x, even the most pathological, except x being a single point. Then there is nothing to really do. Then you just have a vector space, a single vector space, an. Right? Yeah. Okay. Look. Okay. So let's keep going. Maybe I'll make that comment now. Whenever you have a vector bundle, There's actually something called, there's actually one particular subset of F that's kind of canonical. A zero section. Now, what's a section? A section continuous. Remember, F is in your space of objects. Like it's a topological space. It's a variety. It's a scheme itself. So you can talk about regular maps from X to F. You can talk about morphisms from X to F. You can talk about holomorphic maps from X to F if you're in that subject. You can talk about C infinity maps. You can talk about whatever. So a section is a blank map. So I'm just going to call them maps from now on. Is a map back up? Not our, map in your category, in your subject. Is a map back up? Such that when you compose, you come back to the identity. In other words, how do you think of a vector bundle? You think of a vector bundle as a family of vector spaces, affine spaces, ANs, vector spaces hanging above every point of X. And that on certain open subsets of X, you can iron it out, straighten it out into a product. But you're not necessarily able to straighten it out over all of X. You can't trivialize over all of it. And when you compare two straightening outs, there's like still a little twist, still a gluing, but only by matrices between this affine spaces and these affine spaces, like a twisting family of vector spaces. But there's a zero section. The zero section picks out the zero element in each of the affine spaces. Okay, the origin. Okay, so the zero section just sends an element X in X to 0 in AN. Now, which AN? It doesn't matter, because you might worry, like, what if someone chose a different system of trivializations? What if someone chose U alpha? That's an open set around X, and then used this phi alpha and talked about 0 cross U alpha there. But then someone else came and used U beta instead. That's fine, because since these transition functions are linear maps, fiber by fiber, the point 0 goes to the point 0. And so the zero section is well defined. It survives these transition maps. It would not be well defined if you only considered affine linear transition maps. Then you don't necessarily have a zero section. Okay, so the existence of a zero section very much depends on these transition functions being linear maps. Okay, this is well defined. This AN is the one over X. Okay, we talk about the fiber of a vector bundle over a given point. It's a vector space. It has a distinguished zero element, this one, and you can add and multiply, etc. That's why it's called a vector bundle. Okay, family of vector spaces parameterized by the variety X. That's what it is. Okay, so vector bundles have this one particular zero section. Now, from a vector bundle, you can read off a sheaf. So I'm going to do two now. Very good. Good comments. Okay, suppose you have a vector bundle. From this, you get a sheaf on X. We will use the symbol fancy F. And it's called the sheaf of sections. Now a sheaf is like an assignment of some stuff over every open, right? I'm going to tell you what to assign on each open subset of X. For any open subset, any, not your, doesn't have to be your distinguished one that was, some existence statement was the one that was implied in the vector bundle definition. Any old open set, you assign the set of sections. Sometimes people will write just F sub U for this thing. It's the part of the vector bundle living over the open set U. Good diatoms attack. I think what you're here for, actually, let me just get this out of the way. I think what usually what diatoms attack is here for is a shout out. So let's see. Here's your shout out. Okay, there you go. So, okay, so what kind of functions though? Always in whatever subject you're in. Whatever subject you're in. For us, it's regular. Okay, it's a morphism. All right. So it's this set, such that, you know, sections. What do you think of? It's a choice of a vector for each of the points on U, of a vector in the vector space above that point, hanging above it. A systematic choice, a continuous choice, or a regular choice, or a holomorphic choice, or a blah, 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 blah. Okay? Now, this is obviously a sheaf. This data obviously encodes a sheaf. What are the restriction maps? It's just restriction of attention. And how do you create a morphism from some large open set that's made out of small open sets? You create a morphism on the small ones which agree on overlaps. Gluing axiom. Yeah. It's one of this situation is always obviously a sheaf. Okay? So this is a sheaf that comes out of a vector bundle. Now this sheaf looks really, really simple when you look over certain open sets. This is a sheaf of functions, a sheaf of sections. And the whole story is that the vector bundle is encoded by this sheaf. Period. Okay, so just like in algebraic geometry, the physical object, you know, the varieties, were encoded by the ring of functions on them. That's the story of algebra. That's literally the one-line story of algebraic geometry. Don't do math, non-rigorous math with like locations and circling dots and drawing pictures. No. Just take the picture, encode it as a ring, let Wolfram Alpha do your work, and then reinterpret what happened. In the same way, a physical vector bundle is encoded instead by this data. This is rigorous. This is just data, sheaf. Okay. So this data is a particularly nice kind of sheaf. Exactly. The zero section, yes, good. So, we just call it 0. Okay? Yeah, absolutely. 100%. Okay, and we'll do more notation in a second. This F, I want to point out something about this F. What if you were to take this F and look at it over one of those U alphas? Now remember, U alpha has a trivialization. The bundle has a trivialization over U alpha. Whole diagram commutes. Every arrow is in your subject. Okay? All right, now notice, to give a section here is the same thing. There's a dictionary, thanks to phi alpha. There's a dictionary. If I give you a section there, it's the same thing as giving a section to the first projection map on this right-hand side. Same. Like, just use phi alpha to port over sections of one of the maps and sections of the other. But what is a section of first projection? What is a section of first projection? Here's what it is. S prime is the data of n functions. What kind of functions? Whatever your subject is. You got to think about this. How do you provide a section? Remember, you got to send a point P to an ordered pair. But hold on. What's the first entry? It's got to be P again, because the composition has to be identity. So this part is not interesting. And the other part is n different numbers. Now, each of these numbers, this is a number that depends on the point P. That's a function. Okay? Done. So S prime is the data of n functions on U alpha separated by commas. We have a name for that. It's the functions on U alpha separated by commas. Now this is a ring, right? This is just a ring. It's part of the data of the sheaf of functions on a scheme or whatever. You read it off from that part. It's there for you. It's already been in the data of this object that you're studying. And notice that that's a free module over that ring. OX, I just put OX for short, right? Over this open set. And that's what we're saying. It's not just that you have any old type of sheaf, random sheaf on a topological space. This sheaf, if you look close enough on a particular open cover of your object, you are looking at a free module over the ring that comes equipped with your locally ringed space. All right? So that's what we mean by a locally free sheaf. The summary, the point, the bottom line is, it's a locally free sheaf of OX modules. Right? Okay. All right. Okay. So now what I'm going to do really quickly is tell you, if you have a locally free sheaf of OX modules, you will recover the same critical information that's needed in order to produce a vector bundle, or in order to, the same critical piece of information that comes out of witnessing a vector bundle. And then that's the full circle, right? Enough for us. And then we'll witness these transition functions in examples, because that's absolutely more valuable. Okay, so look, suppose now someone just drops a locally free sheaf. F. Okay. All right. What does that mean? I'll tell you what that means. It means that the sheaf is locally on X isomorphic to the direct sum n times of just the structure sheaf, or the sheaf of rings OX. Okay, so it means, let me write it carefully. It means that, first of all, F is a sheaf of OX modules. And two, there exists an open covering. I'm telling you what this means, locally free. There exists an open covering and sheaf isomorphisms If we allow a different set of possible transition functions, it looks like it wouldn't change locally what a section is, but it would change things globally. Yep, absolutely. Absolutely. Okay. So that's direct sum. Okay. There's a bunch of sheaf isomorphisms like this. All right? And these are isomorphisms of OX modules. Sheaves of OX modules. Okay. All right? Got it? That's what it is. Now, what if you have one of these locally free sheaves? What would you do? Well, you can now pass to an intersection. Well, of course, you have F further restricted to U alpha beta, the sheaf. So I'm thinking about all the data on these on the further open sets. Now this was an isomorphism of sheaves, so it keeps giving you isomorphisms here too. The data of an isomorphism of sheaves is like, trickles all the way down, right? And how do these sheaves restrict? OX just restricts to OX of U alpha beta, whatever that was supposed to be. Then you just do parallel computation. So you get this on the one hand, and then you also get the other one. And now, this thing here is a map between sheaves, free sheaves of OX modules. That's given by an n by n matrix with entries in OX U alpha. It's an isomorphism, so it's invertible too. The point is, you pick up the same data that went into the DNA of a vector bundle to start with. This n is the same for all open sets. Exactly right. That's part of, yeah. So it's a rank n locally free sheaf is something such that there's an open cover where locally the sheaf is isomorphic to just the structure sheaf raised to n times. Same n everywhere. Same. Yeah. Absolutely right. But once you have that, those kinds of trivializations of the sheaf, then by comparing two of them, you get these transition matrices. Same data as when you had a vector bundle. Okay? So the point is, vector bundles and locally free sheaves are the same thing, and the easiest arrow is starting with the vector bundle, output the sheaf. The sheaf is just the sheaf of local sections. Okay, so now let's look at an example. An example is going to be worth a lot. Let's look at an example of a line bundle. That's the special case n equals 1. A family of one-dimensional vector spaces parameterized by your variety. It's like someone twirling a baton. Yeah? That's the physical object I'm trying to think about in my mind. All right, let's look at an example. Now, this is probably going to be where I'm going to get, I'm just going to, F it, I'm doing it live. I'm doing stuff that really shouldn't be done live. But let me give you an option. So what I want to do is analyze the universal subbundle, or the tautological subbundle, or the most elegant line bundle that projective space has on it. Well, you don't know that it's a line bundle yet. I'm about to show you that it's a line bundle. We're going to go through the definition or whatever. Okay? So I want to analyze S over PV. Okay, V is a vector space. This was the set of lambda Yes, it's PV equals nRT, absolutely. Okay. All right, so no, we're not going to do was direct product a request? No, direct product, I'm not going to the product with the affine space is clearly a vector bundle. I don't think that's what you're asking. Yeah, not canonical. Absolutely not canonical. Yeah. It's Milner? Okay, I still don't care because we live in the present day now. Yeah, we live in 2020. Canonical is an no, canonical is the top. What is the name of the top wedge of the cotangent bundle then? Let me guess, it's the universal bundle. It's completely backwards. No. Okay, 2021. No. S is Skugget. Projective space is the space of directions through your eyeball, right? S is like shoot a laser out your eye. And just think about that family of lines. One line per direction. That's what S is. The total space of that family of lines. Okay. All right. Anyways, it's this. This is the formula for S. This is a 1D vector space. And you choose a vector on it. Yeah. Right, except the 0 has been separated out for all those lines. A little bit of a in this S. Okay, good. It's actually the blow up of the origin in V. That's what S is. Now, okay, so question for the audience. Do you want me to do this with n-dimensional projective space? Or do you want me to just do it with P1? And then you will believe or figure out how to do it for Pn. Which one do you want? It's a matter of whether you're allergic to indices or not. P1? P1. Okay, P1. P1. Fine. Okay, so n equals 1. Let's choose a basis of V. Okay, 0 and 1. Let's do 0 and 1. Okay? All right, all right. So, okay. So on P1, we have two standard affine opens. I'm just going to tell you that those two opens are going to serve as trivializing open sets. It is not at all obvious, given a vector bundle, which open sets afford a trivialization. In fact, that's a very interesting question. In a sense, that question gives rise to the concept of Chern classes and characteristic classes of vector bundles. Okay? So it's not that every open there's a trivial, or you know what? Throw a dart, that open works. No, it's not. I'm just going to tell you that the standard affine opens are going to work. Look, so let's just write them down first. U0 will be these points. I'm going to use notation that I learned from Vakil's notes. I can't believe I hadn't seen this notation before. And it'll help you write out the general one for PV as well. These are the two standard affine opens, A1s, constituting P1. Okay? Now, A01 is just a number, an element of A1. And A10 is another number. Okay? Good. Now, what am I doing? Right. So now I'm going to write what is the preimage of S over these open sets? So for U0, what is this? It's the set of pairs. It's the set of pairs. The corresponding point in P1, which is just the direction, which is the span of this column vector, A01 with the 1 on the bottom. Just that's lambda. That's the data of lambda, the one-dimensional subspace of V. Okay? Comma, any vector that's in that span. I'm just unraveling what the part of S living over U0 is. It's this stuff. This is what it is. Now look, this is isomorphic to just U0 cross A1. The map is this. if you have an ordered pair like this, just record V2 or V1. I'm doing it live. V2. I gotta send the first part to the first. It's a project. I gotta make the first point go to the first point, right? It's what's happening here. I record just V2, where V is V1 E1 plus V2 E2. V2 is just a number. Okay? Exactly right, Megalomorph. Exactly right. Okay? This is an isomorphism. Because if I just give you V2, the data of V2, that picks out a unique vector in the span of the left-hand linear space that's encoded by A:1. Because what you write here is V2 times A01. That's the only thing you can put there so that the vector V is actually pointing in the direction of your eye. Okay, very simple idea. All right, so that's what phi0 is. So now, phi1. I'm gonna go over here. I'm sorry. I didn't time this right, but I think I shouldn't break here. I should finish this example, say what I want to say about it, and then break. Okay? Okay, so now I'll do U1. I'm finding for you a trivialization. All right? Good. Notice that this assignment, in terms of the number V2 or the A's and the V1 and V2, everything was polynomial expressions. Polynomial, rational, whatever. Okay. So now U1, similarly. All right, I'm definitely gonna make mistakes. So just write what I was supposed to write. You didn't fix my typos. Are you guys asleep? 0 and 1. Okay. Okay. Now I do this. We're straightening out pictorially. S is some twisting family of lines. On these large open sets in P1, we are flattening out S. But as we will see, the thing is fundamentally twisted. We'll build to that. Okay. I gotta trivialize it, right? It's a line bundle, so it's a bunch of A1s. You send this point to the same first coordinate, of course. Okay, Then you read off only V1. No, V0. Wait, V2, what is V2? Oh my god. V0. What is this? See, I knew it. Even with only 2 indices, I was gonna mess up. I can't do anything right. Okay. Okay, I think I got it all good. Now this one's V0. Be very careful. Don't be fooled. Oh my god, this one is not lining up with this. Yeah, no, you gotta be very careful in this business. If you start just thinking, oh no, it needs to be the other way, you are gonna replace what we call the sheaf O of -1, which is what we're witnessing here, with O of 1. Disaster. Total disaster, in fact. Okay. Did I make... In purple? Did I make a mistake? Oh yeah. Okay. So now, you look at the transition map. There's only one here. There's only one transition map to worry about, because there's only one intersection. Thank you for choosing P1. Alright. So now, okay, ready? Ready? Okay. I need to start. I'm doing this transition. U0 to U1's transition. Okay, I'm trying to do that. So I'm going to start at U0's sort of domain here, the chart here. And I start with a pair. Okay, I'm going to write that down now. Correct indices. But I'm only thinking about points that are in U01, which means A01 is non-zero. And then you send that, according to this dictionary, to this particular vector on the right hand side. So this is of course the same point on the side. This feels like doing a homework exercise. It's giving me flashbacks from like college. Okay, then you send this to the same point. Hey Kevin, how's it going? It's the same point. So this point is equal to this one. And then you're supposed to read off this entry, V0. Which I'll write it. Okay, so what's the transition function? It's an n by n invertible matrix whose entries are functions on U01. And it's right here. You read what happens on this factor. V1 becomes A01 times V1. It's not V1 becomes V1 plus 7 or V1 becomes V1 squared. It's a linear map, 1 by 1, just multiplication by a scalar that depends on the point. Okay, so this is the transition function. So now what I'm going to do is a computation. I'm now going to show you that S has no interesting global sections. The computation is written like this. And the way you read it is, this is the word for, this is how you write this, the space, the vector space. Vector space of global sections. It has none. We just say none, even though there's always the 0 section. All right? Now this is going to require the subject to be something, a good subject that makes sense and isn't just all floppy and stuff. All right? So algebraic geometry, in the holomorphic realm, this will be true too for complex geometers. In fact, analytic people will be fine with this. Okay, so there's the problem with flabby subjects like just ordinary topology is there are bump functions. So you can take this 0 section and then just budge it. Just one place. Poke it. I guess technically now you have a non-zero section. Good job. So now I'm going to do this. Okay, in our algebraic geometry, this has no global sections. Why? Because what I'll try to do is take a global section in one chart and see if, when I port it over on the intersection, I get something that extends to a global section on the other chart. And if I can, then the two glue together, and so sheaf, 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 you have a global section. Yeah? So I'm going to do that, just live on TV. Okay, so here's the chart over here. This is chart 1, or chart 0, and this is chart 1. That's right, no non-zero global sections, no interesting ones. Yes, we did. All right, got it? Okay, so what is this chart? This chart is literally A1 cross A1. And I'm supposed to give you a section of that down over the projection to U0. That just means a polynomial in A01 on the right-hand coordinate. Now pay attention. A polynomial has no negative powers. That's not regular on all of U0. Okay? It's not, yeah, I know, megalomorph. Okay. So, yeah, I'm sorry about that. Okay. So, it's a polynomial. No negative powers allowed. Okay. Now you port this over. This is just this number V1. You port it over. You follow it by the transition function. And it will become the following map thing. You're supposed to multiply by A01 times that. But now what's the relationship between the coordinate on U0, which is A01, and the coordinate on U1, which is A10? They are inverses, I'll just tell you. And so if I try to now rewrite the right-hand thing as everything in terms of A10, I get the following. Now the question is this right-hand thing, does it come from a section on U1? Hell no. Hell no. This is never going to be a polynomial in Q unless P was just identically 0. In which case Q is also identically 0, and this is the 0 section. Okay? So that's this calculation. All right. All right. So now, in the last negative 17 minutes, I will ask you to do the following exercises. Whenever you have a line bundle, you get something called the inverse line bundle. or the dual. Okay? I'm just going to tell you how to construct it using transition functions. If G, alpha, beta were transition functions, oh, we say transition functions for line bundles because they're just one by one matrices, little functions. Transition matrices for vector bundles, higher rank. Okay, if G, alpha, beta are transition functions for, then you put G, alpha, beta inverse on the page instead. And then reimagine a line bundle that gave rise to those instead. Turns out you can. And for us, this is homework. Prove. So we write L inverse or L dual for this line bundle. All right, that's what we write. Okay, prove that the global sections of the dual of the tautological bundle is quite large. In fact, it is naturally this vector space. Okay, and this is homogeneous forms, linear homogeneous forms from first semester algebraic geometry. Remember that homogeneous coordinates are not actually coordinates on projective space. They're not functions. What are they? They are sections of this line bundle. That's what a homogeneous form is on projective space. It is a section of this line bundle. And this one we call, in the Sheaf language, O of 1. Okay? So do this, how are you gonna do it? I told you to stick A01 inverse right here instead. Or in that whole system of information for the, when you have larger projective space, you're gonna have to do this on many charts. Stick the inverses of every transition function you're seeing. I'm saying that now try to compute global sections, and you've got all kinds now suddenly. In fact, they're in natural bijection with linear homogeneous forms, homogeneous coordinates on projective space. That's what homogeneous coordinates actually are. They are not functions, they are sections of O of 1, this particular line bundle. All right, if you want extra credit, if L is a line bundle on X with transition data functions G alpha beta, telling you how to glue trivial products together, then you get another line bundle. Just take the nth power of that function. And it's called the nth tensor power of that line bundle. It's another line bundle. Okay? So I want you to do this exercise. This exercise is actually no harder than the one I just showed you, but whatever. Do we need our cameras on for the test? No, I'm gonna trust that you're honest about this extra credit problem. Okay? So, when you were doing algebraic geometry in grade school, and you had, you know, wow, you had some P3 and you were drawing this quadric surface. Oh, whatever. Like, what was this? What was that expression? You were taught, oh, you need to only put homogeneous things down because that's the only way you get a sensible zero locus and stuff. All this garbage you were told and so on and so forth. What it is naturally is that it's a section of a particular line bundle, O of 2, on projective space. It's not a function. It's a section of a line bundle, a different line bundle, a line bundle other than the trivial line bundle, O of 2. Okay? So these line bundles on projective space, you'll see O of n all the time in algebraic geometry when talking about projective space and various constructions. But it's not something to be scared of. What you should understand is that the global sections of those line bundles are these homogeneous forms. And O of negative powers have no interesting global sections. Okay? So have fun with that. And next time, I'll start with what a linear system is. Because once we're comfortable with what a line bundle is, for example, then linear system is just a simple definition. Okay? So that's what we'll start with next time. Sorry about going over, but you don't have to stay if I go over for a stupid computation. Okay, next time. But people that are actually you know, in the seminar on Discord actually do this. If you this is mandatory. You can't continue without it. Once you got to do these calculations yourselves, and definitely not spectator anymore. Here, if you don't do this, this gap is enormous. You won't know what the hell I'm saying. Like, you just won't know. What are you talking about? Yeah. Okay, fluency with vector bundles. Doing specific examples and looking at the transition function. Just do line bundles for now. I'll show you how to make stupid examples of higher rank vector bundles next time. Just a definition. The hard part about linear system is the only new part for some of you is just the concept of a line bundle. Then after that, it's stupid. Okay. All right, let me look at the chat now. All right. Let me roll the credits. Start compiling the credits. Hey, did you all shout out Tayo? Man, my mods. Everyone who streams has to be shouted out. Tayo. Go check out Tayo for all kinds of math fun. Most popular math streamer on Twitch. Possibly even just streamer, period. I'm not sure, I haven't checked. Who else? Megalomorph streams. I just learned that the other day. Also math. Same level of popularity as Tayo. Don't start like ranking people and stuff. Who else? Kappa. Kappa is here. Now Kappa doesn't stream math quite yet, but is currently experimenting with streaming Diablo 1. And I have one of his emotes. Check it out. That's one of Kappa's emotes. It's a rank and math streamer. That's pretty good. Hey, Kevin. Okay, so who did we say there? We said Tayo. We got Tayo. We got Tayo. Okay, I'm not gonna be able to color coordinate. Okay, Tayo. We've got Megalomorph. We see Pandemic. We've got LDW. LBW. He's or she, I don't know. This person is an Australian. Now, I think I know it. I think I know who it has to be. All right. Blur Jelly. Who are you? All these people. Balby. Okay, Balby. Rowowzow. Small. Sommel. Link Michael. Mars. Are these bots? This sounds like bot names. Bots. But new bots. Welcome. Who else is here? Kevin. Kevin does chemistry. I got you. Math teacher now. Congratulations. One of us. You're not a bot. Okay. Isn't that what a bot would say? Kevin, yeah, sorry. Yeah, sorry. Good point. Good point. Good point, AC. AC. Wouldn't have the seminar without AC. And LBW, I suspect. Who else is here? I got Skugget was here. Who else was here? Yeah, I'm sorry I couldn't pay attention to the chat. I was doing an actual example. Can you believe that? Oh, wow. Okay. Kappa Votes was here, and Diatoms. And of course, Kappa. Diatoms. This guy has 2 labs. Not even a joke. Where to find the text? Oh. Yeah. You've missed two meetings. But if you want to follow, is that how you say and? I forgot how to do and. Oh, yeah. And all that. The book by Eisenbud and Harris. But you won't find what I just did in that book. In that book, I will quote you in that book. Language. What is it? Let me read the exact sentence. Let me just say what this whole day was about. Let me see here. My books. Where is it? Language. Yeah. Right. There is a one-to-one correspondence between vector bundles on a scheme X and locally free sheaves on X. I could have just done that. Okay? That was language. That's where we are. We are not far. But I can't be confident that the people I care about wanting to learn are actually get with me if they don't do these exercises. And get just not afraid of what a line bundle is, how to deal with one that's given relatively explicitly to you, like this universal sub bundle over P1 over projective space. Okay, good. Okay, next. There's one more sentence. Oh yeah, there's one more. We will use the terms interchangeably, generally preferring line bundle and vector bundle to invertible sheaf and locally free sheaf. Great. Can you say something about sub-varieties and global sections? Is the zero section a particular instance of such a correlation? Very good. LBW, that's actually a fantastic state. Fantastic question. Sections of a vector bundle naturally produce closed subvarieties of X. If you have a vector bundle, it has that zero section. If someone gave you some other section, or the same section, then you can intersect S with the zero section. okay? Or you can look at S inverse of the zero section. The zero section is actually a closed subset of F. And so you can take its pre-image under the section and you get a closed subset of X. Zero section is a closed subset of F. And in practice, especially in intersection theory, enumerative geometry, most of the sub-varieties that we will be intersecting or thinking about will arise from this very innocent construction. All right, so LVW, this is yes. Actually, X is realized as a subvariety of F via the zero section already. So you kind of have a sort of picture. Not sure why I didn't draw this picture before, but yeah. So by the way, if you choose a silly section, like the zero section, then this is just all of X, right? But in interesting cases, you get different things. So in this example, in this homework example, if you take a section an interesting section, a non-zero section, then it's zero locus, which is often denoted V of S. It's just a section is a systematic choice of vector above each point in X. A vector in which vector space? The one that's the fiber of this vector bundle. Okay? You're just looking at the locations on X that are picking the zero vector. Those are closed subschemes that emerge. And in this case, V of S is a degree n hypersurface. Okay? So you should, and don't believe me, this will come out of just the doing this exercise. And this exercise is just put the right transition functions between trivializations as follow the instructions. Never took algebraic geometry before. It's not common curriculum, I would say, Kappa. It has a reputation of being hard, Kappa votes, but it's not. It's not. It's just it takes some practice, like doing these exercises, to get you comfortable and with the language. Okay. What's the text title? Oh, this. We're gonna follow this text, but understand we're in chapter 0 still. Because without being comfortable at least with the objects in chapter 0, I will be talking to nobody. Or I'll be talking to people who are just nodding their heads, which is the same thing. All right? So this is the book. but we're in chapter 0. After linear systems, I'll just start with, I'll just state, we'll just state the basic results of dimension and smoothness so that it's in front of us once. Take them as facts of life and then move on to chapter 1. Oh, also, can we create all subvarieties of X from vector bundles? That, okay. In a sense, yes. Sort of. Sort of. Yes. Okay, yes. For all the varieties that we ever care about, yes. However, it will end up happening that there will be a notion of a section of a vector bundle meeting the 0 section correctly in the right dimension. There will be a concept like this. And then if you ask, are all varieties obtained by a section meeting a vector bundle in the right dimension, then that becomes a much open-ended, hard problem. Okay? So there's a stupid answer to the question, and then there's like the question that should have been asked. If you realized this concept of a section meeting the zero, having the correct codimension of 0 locus, then it becomes crazy. It's not just transversality, it's dimensional correct intersection. So it depends on what transversality means, but like 2 lines meeting in space is not transverse, even if they're transverse. So it's like a dimensionality, dimensionally proper 0 set. Then the question is fundamentally challenging that LBW asked. And I know that that's a dangerous question. That's the bottom line. That's starting to become dangerous. LBW. But it's a wonderful question. Those are good. That's a good question to think about. Exactly which subvarieties do I get in an abstract algebraic variety from 0 sections of correct dimension 0 sections of vector bundles? I know. Okay, I already know you're not going to get all of them. But still, keep wondering. No, you didn't. Tayo. Oh, that's not Tayo. That's tensors. Okay, yeah, tensors you did. Tensors you did. You missed out. Actually, LBW. LBW. Do you want to know an open problem? Joe told me this problem a couple years ago, and I mean, we were both shocked. Here's an open problem. Ready? Since you're interested in how to create subvarieties of something. Okay, here's the problem. In projective space, is there, when is there, for which N and D, no, not N, M and D, is there a non-degenerate, smooth, degree D, M-dimensional subvariety. This is an open problem. It will be open for a while. D is the degree, absolutely. Degree D. Non-degenerate, don't cheat. No cheating. Another way of saying it is, for which triples M, D, and N is there a non-degenerate smooth degree D? And it's very important that you do smooth. You can do stupid things like, you know, unions of planes and garbage. No, no, no. Irreducible. Yeah, yeah. Whatever. It means it's not contained in a linear subspace. Or there's no linear form in its homogeneous ideal. No linear function form vanishes completely on it. So it's not, you know, it spans all of projective space. It's not like a conic in space. That's or a rectangle for that matter. Fine. Notability. It's not like that. But of course, a rectangle is not an algebraic variety. Hey, Smash Time is here. Doing great work. For as a mod. Amazing. Okay. Yeah, anyway. LBW. The ability to produce subvarieties of a given random variety is one of the most difficult problems or open-ended questions in algebraic geometry. All right? It's basically, in a sense, you can think of it as very, very close. It's one hop step away from the Hodge conjecture, one of the Millennium Prizes problems. Or the Tate conjecture, if you're an arithmetic geometer. It's the more tricks you have of creating subvarieties, the more powerful you are. And vector bundles give you lots and lots of opportunities. Certain ones. For example, not the universal line. That's not going to give many opportunities. Not S, but S dual. S dual is good. it produces hyperplanes. All right. Okay, everyone satisfied? Monday, we meet again Monday. The serious members do these. You have to do these, otherwise, I'm not convinced. All right, good. We'll do more linear algebraic operations on vector bundles next time. I'll show you a rank 2 bundle if you really want to see one, and then talk about the concept of a linear system. All right, good. I got Vixen, right? I always get Vixen. Oh, I didn't get Vixen. All right, who are we going? Who are we going to? Where are we going? Who's on? Who understood and started correlation of subvarieties and vector bundles? Probably Sarah. It's probably, if you really want to put a name to it, it's probably Sarah. That's probably the first name that comes to my mind. The relationship between subvarieties and vector bundles. I think it would be Sarah. I did Smash Time. I did. He complimented me on a talk. It's the highest point in my life. However, it happened in a bathroom, so let's not talk about it. It was kind of awkward. Anyway. That puzzle guy, Femvox? Seems to be a pattern with you, Femvox. LBW. Yeah, I answered that question. Okay. All right. Ready? Oh, by the way, also Smash Time. This was before you came, I think. Yeah, because it was my first year. My first year? Kate and Mazer gave a course on what? On algebraic number theory and class field theory. And I didn't like it. But in retrospect, I feel so bad about not liking it. Because I mean, how spoiled can you be? Like Tate himself teaching us group cohomology and the transfer map. Okay, it's just traumatic, but I just wasn't ready for it, I guess. Yeah, so yeah, I spoke to him then too. Anyway, there's regrets. I should have paid more attention. Okay. Are we gonna go to another puzzle place? Femvox, you're the one that's suggesting, so let's go, Femvox. Yeah, oh, final question. Yeah, go. Oh, procrastination is here. Yeah, LBW, what's up? Final question. Go ahead. Yeah, exactly. Good. Yeah, we'll go, Femvox. We'll go. Sounds crazy. We'll go. You're missing a link in between those. You're probably missing the backwards link. I showed you the forwards link. Ah, which came first? I guarantee you the geometric one came first. I think the person who first did that was Sayre. At least totally, completely. Yeah, I don't know. The more you learn the history, the more and more, maybe you already have it, but Sayre was, I don't understand how Sayre, like, no words. Okay, that it was in the 50s, if I have my history right. I'm teaching history of math next fall, so I should get this right. But yeah, LBW. But always the geometry comes first. That's the pattern, and then someone has to make it, like, ground it in something that's not just always hand wavy. Oh, budge the vector like this and then do that. Oh, now imagine it and take some LSD and then no. Write it down. Encode it rigorously. Then you get a variety is not just, oh, just draw this picture. Oh, yeah, it's okay. You just sculpt this and then take a picture, put it in your paper. No. This is a ring. The ring of functions. All right. The vector bundle is its sheaf. It's held by its sheaf of sections. All right. It seems it's more of a it's more of a sort of, yes, a languageization. But languageization is good when you're trying to make things rigorous. It's just the pattern of the subject. When you try to, like, make things, when you try to encode a geometric thing by a ring or a module, now you're in commutative algebra. And I bet you feel safer in commutative algebra than in 1800s Italy, where it's just like, oh, now just by the principle of constancy of this, this curve becomes this parabola, and it's this. Intuition-wise, of course you prefer geometry, but how do you know what you're doing is right? And Italian algebraic geometry started to get corrupted slowly, and people realized the need to encode the objects in commutative algebra. That was Zariski's deep, major life work. Zariski is the one who was trained by the Italians, saw the need for replacing the thing with the ring, the vector bundle with the module, and then phrase everything in terms of, as much as possible, in terms of just commutative algebra. Yeah. There's another advantage to doing this languageization, as you put it, LBW. It's because it unifies parts of math and makes it less surprising. For example, the story about the class group of a number field is actually just the study of line bundles on a different scheme attached to that number field. But you only see that through the language. So that you start to see analogies between fields, but only after the languageization. Someone gives you a class group, you don't suddenly see like a family of lines swiveling around, but it's there if you look carefully. No, it was. It's part of the motivation. It's part of the motivation, LBW. There are places where vector bundles show up, which they're not in reference to any sub-varieties, for example. For instance, when when someone studies space-time and general relativity and all this,
Yes.
they need to talk about the tangent bundle of a manifold. And then on it, they're going to put a structure of some metrics of some different types, right? So the concept of a vector bundle, this tangent bundle, had its own intrinsic merit. It wasn't about finding subvarieties necessarily. So that goal of studying vector bundles has its own independent concept of vector bundles isn't just attached to the hunt for subvarieties. It's very intimately linked to that in algebraic geometry, but it's just one instance of the general importance of the concept of a vector bundle. I don't know if that's what you were asking, but yeah. Yeah, no. Vector bundles show up in different places for completely different reasons, and I'm just telling you what it is for our seminar, our topic. Why we'll need them. Now, okay. So Femvox wanted to go somewhere. They probably already went. So what was this? What was this place? Let's go check out this person. He won the American crossword puzzle tournament several times? Okay, this is gonna be insane. Femvox. That puzzle guy. Alright. Go spread the love. So it's a miracle to see that global sections of not a rank. Oh, sorry, one word. LBW. It's not a rank n bundle. That's a tensor symbol. It's a line bundle. LBW. Do that exercise carefully. It's still a line bundle. That thing I wrote down. I didn't put direct sum. I put tensor product. Okay, but yeah, it's cool to see that connection, LBW, and it's important that you understand it. Okay, let's go. We can continue on Discord, LBW, and we should. All right. Okay, everyone. Thanks for being here. Oh, look at this awesome group of people in this seminar that is starting to pick up some temperature. But please, I'm just trying to get it so that enough people understand the language semi good enough before we dive right in. Okay, let's go.